Well, let's finish this calculus chapter. So lesson 12.6, the fundamental theorem of calculus. And where we're going to pick up is this bell ringer. Last class we learned how we could approximate the area of a graph of a function between the function itself, or the curve, and the x-axis on any interval. And so I kind of built a calculator for us last class, and you can find this if you just go to your calculator list at the very bottom. You'll see that link. And to show you how it works, what we're going to do is type this equation in as f of x. So I'm going to have negative 1/3 x squared plus 2x plus 1. And we want to estimate the curve, or the area between 0 and 5. So right here on the A and the B, I want to put that to 0 to 5. And so last class, what we talked about is there different methods of going about this. We could do what's called the Right Riemann Sum, which is basically you're adding up these little rectangles, and you take the right endpoint all the way through, and I need to add the 0.5 on here. So from 0, or we actually would start with the rectangle that completes at the x value of 1, and then 2. And this is if you had a width of 1, and you would find the area of each rectangle, multiply them out, and you would come up with your area. So in this particular case, we would be adding the areas of 1 times each of these amounts here listed. So it's like 2 2/3, 3 3/3, 3 2/3, 4, 3 2/3, 2 2/3. You would add those up for your total area. And as the lesson went on, we learned that you could do that's a right Riemann sum, is what that is. And we could look at it as a left Riemann sum, where you're taking the points on the left side, and you would add up these rectangles. And then finally, when we got clear to the end, we got the formula for how to get a better understanding of the area by shrinking the width of each one of these Riemann sum rectangles. And so if I go to right Riemann sum first, when I click this, you will see that the area as shown here, if I added up those 2/3 I was talking about, is represented at this value. It'd be 16 2/3 if you added up these values from 0 and where'd my 5 go? There it is. If you added up 2 2/3 plus 3 2/3 plus 4 plus 3 2/3 2 2/3, you should get 16 2/3. That would be the value there. But you can see that this area will not be accurate because we're missing some space over here. And on these 3 blocks, we have extra area added in. And so the exact answer we learned is by using this integral. But what I want to show you what it does is basically the theorem that we learned about last class is it starts shrinking these rectangles to make their width smaller and smaller and smaller. You might have saw I just changed that letter to a W for width. And what happens is the smaller that the width of each of those rectangles gets, the closer the area to being exact, the area under the curve. As you can see, as I make this smaller and smaller, it becomes more and more accurate. Now we're getting really, really close. And I'll go as small as it can. And you can see this looks pretty well like the actual area. And that's basically, in essence, what happens when you take an integral. It just shrinks these rectangles from being 1 unit long, or however long you start, to as small as possible, infinitely small rectangles, if you will. And that's how it calculates the area. So in this particular problem, we should get the answer of 145/9, which if I turn off the fraction is 16.1 repeating. So the answer would be C here. And as a reminder, if we took the right Riemann sum with blocks length of 1, that's what that 16 2/3 would have got us, which would have been an overestimate. And so now we'll try number 2 here. It says the garden in the shape of regions shown below. If each unit in the coordinate system represents 1 foot, approximately how much area does the garden contain? It'll be square feet because it's feet times feet, which is feet squared. So here's my curve. I'm looking for the area under that curve. So I'll come to my equation up here. It's 1/2 x plus 4. And it looks like we're looking on the interval from the x value of 1, 2, 3, 4 to 5. 1 to 5. So I'm going to change my A here to a 1. Okay. And so there's my right Riemann sum. Whoa. There would be the right Riemann sum estimate. And this would be adding up the areas starting from the second from the x value that ends in a 2, 3, 4, 5. And so you would be looking at starting the 2, 3, 4, and 5. You'd be adding these together. That's 21, 33, 46, I believe. Let's check that. Well, why is it saying this? I'll have to check through to make sure. From 2 to 5. So this would be 1 times, it has a height of 5 here. So 1 times 5, that would be 5. So I'm not sure exactly. Oh, I see what I did. I did need to correct this math. This should be W minus A1. That'll correct the math. There we go. And so now you can see the correct values that you'd be adding together. You'd be adding 5 plus 5.5. That's 10.5, 16.5, 23 even. And that's where it gets that value. Okay. And that would be the width at 1. Now, if you wanted to approximate what's the area, if these blocks got infinitely small, what would happen is you'd have this, and you'd have to, if you're going to use the table, add in all the values in between, which we're not going to do. What I'll just show you is the actual value would be 22, not 23, but 22 feet squared. And that would be our answer. So last class, we dealt with using technology to find the integral. What could we do if we don't want to use technology to find the exact value of the area? Is there a rule for it? Yes. It's by using antiderivatives, or more specifically, the Fundamental Theorem of Calculus. So let's first talk about what an antiderivative is. We've learned about a derivative. Whenever you want to go from an equation, you find the derivative, which would be the velocity or the rate of change from that position function. Well, what an antiderivative do? Well, it'll calculate, this is the Fundamental Theorem of Calculus, so I'm not there yet. It'll help us calculate the area under a curve. So here's the antiderivative. It's basically going the opposite of a derivative. The antiderivative is the opposite. So if f of x equals x to the power of n, then this is the symbol for antiderivative. That right here is the antiderivative symbol. Antiderivative. What will happen is, instead of the power decreasing by 1 and multiplying, and the original power multiplying the constant or the coefficient in the front, what's going to happen is kind of the opposite. The power will increase by 1, and you will divide by that power increased by 1. And there could be some constant on the outside, which we'll represent with the plus c. So there are some rules here, as you see, that if you have a coefficient of k already in front and you want to find the antiderivative, you're still going to divide by is the power plus 1, and you will raise the power. Okay, and also the sum and difference rule. If you have two functions, say f plus g, then the antiderivative would be the antiderivative of f plus the antiderivative of g, and so on. So let's take a look at some of these. If we want to find the antiderivative of f of x here, well, here's what we know. The antiderivative will be equal to, so this x has a power of 1. It'll be x to the power of 2. So you'd have a 6. And since I'm raising it to the power of 2, I need to divide by that power I just raised it to. So I would divide by 2, which is equal to 3x squared. And so that would be my antiderivative in very specific forms. But there's one problem, and that is that we could have a constant. You might have saw that this included the plus c. There might be some constant that we don't know about. So to find, that is a antiderivative right here. All antiderivatives would be summed up by saying plus c. The antiderivative, so the capital F of x, would equal 3x squared plus some constant. And c represents a constant. So you could write it in either form there. All right, so here's part B. And again, it says find a antiderivative. So that means you don't have to have the plus c. For f of x equals -6, x to the power of -7. Now, let's walk through this one a little bit slower because we're working with negative powers. So we have -6 x to the, and I'm going to do this in parentheses here, -7 plus 1. And it might help to see a number line. So here's 0. And if we want to go to -7, 1, 2, 3, 4, 5, 6, 7. There's -7 right there. We're starting here, but we're moving 1 positive. We're adding 1, which means we'll have the value -6. So, oh, and I need to divide here. by the negative 7 plus 1. That's the rule. You divide by that same power that you're raising it to. So what does that mean? I will have negative 6x to the negative 6 divided by negative 6. Now, the division of negative 6 will simplify the coefficient of negative 6 in the front, which means my answer is x to the negative 6 power, or 1 over x to the 6. That's another way of writing that. So that is a antiderivative. Now, if you want to find all antiderivatives, you would need to include that plus c. And antiderivatives, I'm not spelling that right. That needs to be a V. There we go. All antiderivatives would look like this. F of x equals x to the negative 6 plus c, or f of x equals 1 over x to the 6 plus c. That's how you would write it if you wanted to find all, which is the better way of writing it like this. So that's why I'm writing it here, even though it just says find a, which means just for one of them, this would be like a constant of 0. There's nothing added to it. So with that, I'll let you try to find a antiderivative, which means you can have any constant at the end. Doesn't matter what it is. So you're really making sure that this portion, when you take the antiderivative, is correct over here. Remember, this is the same thing as saying negative 4x to the negative 5th. All right, I'll let you work from there. Pause the video if you need more time. All right, so now let's take a look at example 2. It says find all. So when it says all, that means I need to have that plus c. It's going to be the antiderivative plus c to find all. So here we go. We have defined the antiderivative here. I have 3x, and it's going to be 5 plus 1, which is going to be the 6th power. So the 6th power, but since I'm raising it to the 6, I need to divide by 6. And this will simplify to be 1/2, because 3 divided by 6 is 1. Same thing as 1/2 to the 6th power. I would add in the plus c for my equation. Let me do it separate. So to find all, let's say f of x equals 1/2 x to the 6th power plus c. This represents all antiderivatives. I'm going to have the plus c. Now let's take a look at part B. Again, it says find all. So I'm going to have capital F of x equals, and I'll rewrite this is the same thing as 4 times x to the negative 6th. So 4 times x to the negative 6 plus 1. I will divide by negative 6 plus 1. Negative 6 plus 1 is negative 5. It does not appear to reduce. So I could write the answer that way, but I'm actually going to convert this back, and I will say f of x is going to equal a negative power in the numerator. It's the same thing as that power being placed in the denominator. So it'll be 4 over negative 5x to the 5th power plus c. And that would be my answer here on example 2b. And let's now check c. So it says find all. So remember, that's going to be a plus c. So this time we have a polynomial. And so to find f of x, what I'm going to do here is I first have x, and it's going to be to the 3rd power. I'll increase it by 1. I need to divide that by 3. Plus 3x. This is going to increase in power. It was a 1. It's going to become a 2. So I need to divide by that power 2. Plus, this is the same thing as x to the 0. So it'll be 4x to the 1st, so I need to divide this by 1. And then the constant that we don't know about will end up adding a plus c at the end. And so when I write my answer, I'll write it as 1/3 x cubed plus 3/2 x squared plus 4x plus c, some constant. That would represent all antiderivatives. If you just needed a or an antiderivative, you would plug in a number there. You could do like 0, which means you could erase it, 1, 2, 3, whatever number you wanted. But to find all, you need to represent it with the plus c. It could be any constant at the end. This would be my antiderivative. All right, now I'll let you try one. Pause the video if you need more time. You are seeking to find all antiderivatives. All right, an indefinite integral. So an indefinite integral of f of x is defined by the integral of f of x dx is equal to the antiderivative of f of x plus some constant. So f of x is the antiderivative of lowercase f, and c is any constant. So the integral of f of x dx equals the antiderivative of x plus f of x plus some c. All right. So I'm going to get to where I explained last time. What does dx represent? And I will show you as we go. So it says here a cliff diver is diving off a cliff that is 100 feet high. His instantaneous velocity can be defined as v of t, where t is given in seconds and the velocity is measured in seconds. Find the position of the diver. Now here they use the letter s of t. This is going to be the antiderivative. Now I know this, and I will show you visually how I know this in just a moment. But here's what we know, graphically speaking, is there a person is going to jump off a cliff into water. Or not, so that's important to throw in there. They're 100 feet high. And if you ever were to jump off a diving board or anything else like that, we know that our fall would be represented kind of like by a parabola. You'd fall on something like this, and you pick up speed as you go. So this would be the idea until we hit the water. Okay, so there's our x-axis, there's our y-axis, and this is measured in feet. And this will be in time, which would be seconds. Let me just put here seconds. Okay, now with this information, they give us a velocity vector, which is saying, or velocity function, meaning that's how fast, if you know how long they've fallen, you multiply it by -32 and you'll figure out how fast it is. Now this is linear, which means it can be changed at any point in time. So the more time goes on, the faster it's going to fall. So at this time, this is using the tangents. After a certain amount of time, you'd be falling at this speed. At right away, you would be falling a lot slower, like if you first jumped. You'd be falling slower, but by the time you get down here, you'd be falling a whole lot faster. Like the tangent right there, you'd be falling at a lot higher velocity. Now that's the velocity. What the position is going to be is the antiderivative of this. And we're going to walk you through some of this as we go. So s of t is going to equal the antiderivative, all right, which you can represent by the integral of v of t dt. And I should say s of t plus c here. S of t plus some constant will equal the integral of v of t dt. Now, honestly, so you might be thinking, what is that dt? Well, I'll go ahead and tell you. It's the change in time. Basically, what you're doing is you're multiplying the velocity times an increment of change in time. And so when you multiply those out, you get area because you're really multiplying. V of t represents the y, a y times an x, and anytime you do that, you're going to create the area because it's the length times the width. And so that's why the d of t, what that represents, and why this represents a shaded, when we did last class, a shaded area in between. That's kind of the math behind the madness here. So let's go ahead and find our antiderivative. So if we know v of t is -32. What we're really looking for is the integral of -32t dt. And so to find this, the antiderivative, t is a power of 1 here, so it'll be -32t to the second power. So I need to divide by 2. And when I do that, this would simplify to become -16t squared. Now that's s of t plus c, which since it's a plus c, I know you would think of subtracting t to right across, but this would represent just any constant value. So it doesn't matter if it's positive or negative on this side. If you're like, wait, why not? Well, because it's a constant, it represents just any random constant here. So I could say minus c, but honestly, there's no difference between a minus c and a plus c because that's representing some unknown value. So it really doesn't matter. But if it makes more sense to you that way, I will leave it like that. Now, what do we know about our constant? We know the constant happens to be 100 feet. That's where we drop from. So my actual position vector would be, and again, like I said, it doesn't matter if this were negative or positive. This is irrelevant. That symbol is irrelevant. It's going to equal negative 16 t squared plus 100. Now, I think earlier I created a calculator for it, but I don't know if I listed it, so just hang on 1 second. Okay, what I just did here is I graphed my the position function that we just found for the cliff diver, and I've graphed what is the velocity, which I'm telling you is the derivative. And how do I know it's the derivative? Well, if I graph here v of t plus s of t, let's see if that'll, and place that up here. No, let me do it with an A. Hang on 1 second. Sorry, I'm gonna hope this will work. Well, I can't seem to exactly figure out how to get what I had going before the last time I showed you, but this was representing the position. So S of t is representing the position of the diver, and this would be representing the velocity. The longer he falls, the faster he's moving. So at 1 second, he would be moving at negative 32. That's what that value is. I just know because of the equation. Negative 32 feet per second. After he's been falling 2 seconds, though, he'd be falling faster. At 2 seconds, he's falling at a velocity of negative 64 feet per second. So he's falling 64 feet per second after 2 seconds. So he's speeding up as he goes. So here's his position, and it's represented by this parabola, but his speed is increasing linearly or decreasing linearly, you could say, because he's falling. So he's falling faster, faster and faster, faster the more time goes on in a linear pattern. So that represents, this would be the velocity vector is always a derivative of the position vector, and the antiderivative of the position will actually give you the area, the total amount fallen, if you will. So that's what we're kind of calculating as we go. So now let's go to part B. It says a cliff diver is falling off a cliff that's 100 feet high. Its instantaneous velocity can be defined by this equation, where t is given in seconds. The velocity is measured in feet per second. Find how long it'll take for the diver to reach the water. So now that we know the position vector, we have that the position vector s of t equals negative 16 t squared plus 100. To find when we hit the water, that means we want to know when that hits the ground here, which would be a height of 0. So S of t is the height. It's like y. So you'd be solving this equation, negative 16t squared plus 100. And so I would need to subtract 100 from both sides. I do not have to do x method here because I do not have a b. So I can just use the square root method to solve this problem. What I call it anyways. I'm just solving using basic algebra. This negative 16 is multiplying, so I will divide by negative 16. So 100 divided by negative 16. Let's see what that is. Negative 100 divided by negative 16 is going to be 6.25. And I believe that's the square root of that is going to be 2.5. I think because 25 squared is 625. I'm going to go ahead and guess. When we take the square root here, typically we would say plus or minus, but since we're dealing with time, time cannot be negative. So I'm not going to actually take the negative. I'm going to say that one's out. And so it'll be the positive. And so t is going to equal, I'm going to guess 2.5 seconds. And I'll just click here on the calculator to make sure. Yeah, 2.5 seconds. So that is correct. That's what it shows here. The position, square root, if you don't believe me, square root of 6.25 is 2.5. So yep, that was the correct answer there. All right, now it's your turn. Go ahead and take a try, see what you come up with. Pause the video if you need more time. And so now let's get into the fundamental theorem of calculus. It says this: if the integral from the bounds of a to b, or on the interval a to b of f of x dx equals, and here's where we do a little substitution. It'll equal the antiderivative solved at the value b minus the antiderivative at the value of a substituted in. So that's how we're going to solve these integrals without using technology. It's the antiderivative, the difference of the antiderivative evaluated at b minus the antiderivative evaluated at a. The top of the integral minus the bottom, or the right bound minus the left bound. And it'll be represented using this form. Okay, so here we go. Use the fundamental theorem of calculus to find the area of the region between the graph of y equals 5x to the fourth and the x-axis. And so before we actually even do this, let's just make sure we get the right answer. Let's see what the calculator has to say about this one. So I'm going to open this back up. We're looking for the integral, or on the interval from 2 to 4 of 5x to the fourth power. So that is what we're looking for. And I need to zoom out here. It looks like I need to be up at least, let's just say 900. And I'll make this negative 100 so we can see below. And I don't need to worry about going so far left or right. So I'll zoom in. And that's the integral we're kind of looking for here. There's, well, there we go. So I'm looking for the interval, or the integral going evaluate from 2 to 4. So that's basically what we're going to do. This says the answer is going to be 992. Let's see if we get the same thing. So if f of x equals 5x to the fourth, then our antiderivative would equal 5x to the fourth plus 1, which 4 plus 1 is 5, divided by 5. Whoops. Which will just be x to the fifth. And normally we would add the plus c, but when you're evaluating an antiderivative, you don't have to worry about the plus c. You don't need that. And so, f of x evaluated from 2 to 4 is going to equal, what we'll do is we'll plug in a 4 first, 4 to the fifth power, and then subtract 2 to the fifth power. So I took this equation and I substituted 4 into it, and then I'm going to subtract and substitute the 2 into it, and we'll evaluate this. Four to the fifth power minus 2 to the fifth power, and we do in fact get 992. That would be our solution here. Now part B, we're going to evaluate this function here. So let's first start with the antiderivative. So f of x equals negative x squared plus 6x plus 9. So the antiderivative, we got to go to the third power. So it'll be negative x to the third divided by 3. Plus this will go to the second power, 6x squared divided by 2. And this is like x to the 0, so it'll become 9x to the first power, which means I divide by 1. So what we'll do is we'll evaluate this antiderivative. Again, we don't have to worry about the plus c. When you evaluate your antiderivative, you don't have to worry about that, from 0 to 6. So I'll plug in 6 first, negative 6 cubed over 3 plus 6 times 6, and I should have probably put that in parentheses right there, squared over 2. I didn't reduce this. Let's reduce what we can reduce right here to a 3. And okay, which is going to now reduce, whoops, this portion right here. Where now we'll have, and I'm going to fix this over here, that looks pretty ugly. Put that there and the negative up front. Okay, we will now have 3 times 6 squared plus 9 times 6. And then we need to subtract a whole group. So I'm going to put that in parentheses. It'll be negative 0 cubed. I don't need to worry about that in parentheses. Plus 3 times 0 squared plus 9 times 0 to the first power, which all of this, anything multiplying by 0, which each 3 terms are multiplying by 0, will disappear. And so that'll just be 0 across. And so this ought to be our solution here. let's see what we get first using, just start typing in what we think that algebra should look like. And we'll test our work. Divided by 3 plus 3 times 6 squared plus 9 times 6. This is giving me 90. Let's determine now if that's totally accurate. We have negative x squared plus 6x plus 9 as my original function. And I'm looking at the integral evaluated from on the interval 0 to 6. And it does say it's 90. So we got that correct. So the answer here would be 90. Now it's your turn. You can either use the algebra using the Fundamental Theorem of Calculus or a calculator to come up with your exact answer evaluated on the interval from 0 to 2 of this function. Pause the video if you need more time. Example 5. Let's walk through some of these, going a little bit quicker. All right, so this is an indefinite integral. That means there's no intervals. So in general, what you would do is we're going to say like this is f of x here. That is f of x. So I want to find the antiderivative would equal x to that's the third power, so it would become the fourth power divided by 4 minus 2x. This is the first power, so it needs to be squared. So I divide by that power 2. This does not have an x at all, so it'd be x to the first. And since it's x to the first, I divide by 1. And if you're evaluating an indefinite indefinite integral, you need to add the plus c on the end. And so our answer here, let's see here, would be 1/4 x to the fourth power minus x squared plus x plus c. That would be our indefinite integral right there. Now, having found that on part B, it says, let me copy this. On part B, it says to evaluate it now from 4 to 1. And so what's different on part B is I would need to plug in the values 4 and 1. So let's evaluate this. F of x evaluated from the interval from 1 to 4 would equal, you'd first plug in a 4, 1/4 times 4 to the fourth power minus 4 squared plus 4. We really don't need the c. If you include a plus c here, when you subtract the next portion, that'll go away. So I don't need to include that. And now let's plug in the 1 across. So 1/4 times 1 to the fourth power minus 1 squared plus 1, which I don't need that in parentheses. It's not even multiplying with anything. Okay, and so if we evaluate that, we should get our answer. So I'm going to first type this in up here, x cubed minus 2x plus 1. And we want to evaluate the integral from 1 to 4. The calculator says that answer should be 207/4. We'll wait and see what that actually is. Now let's type in what we think the answer should be. 1/4 times x raised to 4 raised to the power of 4, not x. Let me take that away. 4 raised to the power of 4 minus 4 squared, which would be 16, plus 4 minus, and we'll put all this in parentheses, 1/4 times 1 to the fourth power, which is still 1, minus 1 squared, which would be minus 1, plus 1. 51.75, which is 207/4. So we did do this one correctly. 207 divided by 4, or 51.75 is the answer here to part B. That would be a definite integral. A definite is when you have an interval listed. So now I want you to solve for first the indefinite integral, and then the definite integral evaluated from 0 to 3. Pause the video if you need more time. Example 6. Now let's take a look at a real world example here. It says the work in joules required to stretch a certain spring is given by that integral. How much work is required? Okay, if I wanted to use algebra and do this by hand, I would need to say that, okay, 60 times x is my function f of x. So that means the antiderivative would be 60x. Now, it was the first power, so now it's the second power, divided by 2, which is the same thing as 30x squared. What I would need to do to solve this one is evaluate this integral, or evaluate the antiderivative from 0 to 2.5. So it would be 30 times 2.5 squared minus 30 times 0 squared, which 0 squared is 0 multiplied by 0. That's going to go away. So this will be 30 times 6.25, which is going to be just under 200, I believe. So let's go see what we get here. 30 times 2.5 squared is 187.5, which we could get that as a fraction if we like, which is 375 over 2. And we'll say that's the answer. Now let's check it with the calculator. If my original function was 60x, and so we're looking from on the interval 0 to 2.5, which we're told is 375.2. So we did get this correct. Now here is one for you to try. Pause the video if you need more time.